My name is Nick Howard, and along with my partner, Carmine Murator, our sponsor, AeroGear, and our faculty advisor, Professor Ryan Cooper, we form Team ME02, and we are in charge of gear residual stress measurement. A little bit about our sponsor, AeroGear. AeroGear is responsible for producing aerospace precision gears and gearbox assemblies. They produce these components for companies such as Pratt & Whitney, Sikorsky, and Boeing, and are considered a leading company in precision gear manufacturing, capable of grinding their gears to within 1/10,000th of an inch. This company is based out of Windsor, Connecticut, and has a workforce of roughly 180 employees. Another company that we had the pleasure of working with in our senior project is TEC Materials Testing. They're responsible for providing solutions for X-ray diffraction testing. They work with companies in the automotive, aerospace, power generation, heavy machinery, medical technologies, and infrastructure industries, and are capable of analyzing residual stress as well as retained austenite using advanced X-ray diffraction techniques. This company is based out of Knoxville, Tennessee, a little bit further away from us. The objective of our project is to measure and develop a relationship between gear grinding and residual stress on a representative gear tooth geometry. To better understand our project, it is first necessary to understand what gear grinding is. Gear grinding is one of the final steps in precision gear manufacturing that is done at AeroGear. Gear grinding is done by a grinding wheel, removing a portion of the surface material from the part that is being manufactured, in this case, another gear. The goal of gear grinding is to ensure that the gear teeth have the correct geometry, as well as a minimal amount of surface imperfections. The other important part of our project is residual stress, specifically the ones that are inside of the gears. The majority of gear teeth cracks and failures are due to root fillet tensile stresses. Compressive residual stresses lower that overall tensile stress when the gear is being utilized. Essentially, you increase the amount of compressive stress that is in the gear already. You also increase the amount of tensile stress that can be applied to the gear without failure. Gears that are produced should already have compressive residual stresses in them from the heat treating process, but the gear grinding process should do even more to be able to improve upon those existing stresses.
Diffraction to determine the residual stress in the gear. The distance between parallel planes of atoms can be found using a measurable diffraction angle and Bragg's law, where lambda is the wavelength of the X-ray, d is the distance between parallel planes of atoms, and theta comes from a measurable 2 theta, which is the angle between the extended incident beam and the diffracted beam seen in figure A below. Two measurements are taken at different angles of psi, which is the angle between the surface normal and the angle bisector of the incident and diffracted beam seen in figure B. These values for distance are plotted on a graph versus sine squared psi, similar to the graph shown. Stress is solved using this equation, where the slope of this line is input here. This d in the denominator is the y-intercept of the graph, and here we have Young's modulus and Poisson's ratio for the specific lattice planes we are looking at. See one of our samples set up for X-ray diffraction at TEC, with measurements being taken parallel to the root and perpendicular to the root. Measurements were taken at the surface and at a depth of about 50 microns for a total of 4 measurements for each sample. As you can see, our samples had to be sectioned in order to properly get X-rays into the root of the gear. Here we have our preliminary results, which we have just received from TEC, and we will be meeting with AeroGear and TEC in the near future to discuss exactly what we are seeing.